Hi, Paul.
Hey there, sorry about that.
No, that's my fault. I was late. It was hard getting around on these icy roads.
Yeah, I can understand.
Um, this is odd. I got you logged in twice.
Oh, really?
Uh-huh.
Oh, let me close one of the windows.
Yeah, I got you logged in to go to meeting twice.
Okay, is that better?
Yeah. Well, I don't know that it really matters. I guess it's okay to have two people in the meeting, even if they're the same one. Uh, but as long as you can hear me and I can hear you, that's what's important.
Yeah, everything seems good.
Okay. So what are we doing? We reviewing for AP Calculus yet?
Yeah, so I was thinking, we're just doing a lot of reviews, so I was thinking, could we do some, like, rotating functions across the x-axis and finding areas and stuff like that?
Sure. Go ahead and give them to me.
Alright, so you find an example.
So you're finding volumes of solids of revolution?
Yeah.
Okay.
Alright, so I guess, section 7.3, on page 390, problem 1.
Hold on.
I guess this is more across sections, but
Section 7.3. Which problem?
Problem 1.
At the back. This is the solid lies between plane lines.
Yeah.
Okay, this is cross sections. And I'm going to suggest we don't do problem 1 first.
Okay.
And we've actually done all of these. We've done B. We did A, B, C, and D.
All right. I guess I didn't read the problem carefully.
Now, that doesn't necessarily mean we don't want to do it again. If you don't know how to do it, we should do it again.
Maybe we can do like just section A so I can refresh my memory. Or part A of that.
Problem A? Okay. So, problem A, the base is a circle. And the cross sections are full circles, like they've drawn it here. Okay? So we want to figure out the area of each of those circles that are the cross sections and sum them up along the x-axis. In other words, we're going to integrate this thing along the x-axis, right?
Mm-hmm. So
this top circle here that I've drawn here, what's the area of that circle? What is its radius? So I'm going to say the area of the cross circles as opposed to the base. So what is the area of any particular cross circle?
It'd be pi r squared, and then
Okay, what's r?
The radius would be it'd just be half of whatever the
radius would be determined by the y measurement of that base circle, right?
Mm-hmm.
And do you see that? In other words, if you look at the brown circle, every brown circle's radius is the y measurement of the base circle. So if we solve that equation of the base circle for y, it comes out to be y equals the square root of 1 minus x squared. So that's the radius of each of our cross-sectional circles. The reason I don't like doing this is because it's just too confusing talking about circles, circles, and more circles. Whereas another problem where you have squares and circles, at least then it's easier to talk about. But so if this is our radius, then when we square it, we get this. So now the area of each of our cross circles is pi minus pi x squared. And we're going to integrate those. Where do they go from? From where to where?
Negative square root of 1 minus x squared.
Well,
to
negative 1. In other words, if you remember, we're integrating along the x-axis because that's the thin part of the cross-section circles. Wherever the thin part is, in this case, it's along the x-axis. So we're going to integrate along the x-axis, and we're going to go from the far left point on the x-axis to the far right point on the x-axis, or minus 1 to 1. And what are we going to integrate? The area of each of these cross-sectional circles, which is pi minus pi x squared. And that's an easy integral to do.
Right.
So integrate that for me.
Okay. It would be
Now one thing, let me just state one thing before you integrate it. Because everything is symmetrical here, I know that if I go from 0 to 1 and multiply the whole thing by 2, that it's the same answer. Wouldn't always be. In other words, if our base circle was not symmetrical about the origin, I could not do that. But as long as that base circle is symmetrical about the origin, I know that the volume of those cross-sectional circles from 0 to the y-axis is going to be the same as the volume of them from the y-axis to this right point on x. So it's actually easier to do it this way rather than going from minus 1 to 1. Let's go from 0 to 1. Makes evaluating the integral a little easier. So first integrate this function for me.
All right, so it'd be pi x minus pi x cubed over 3.
Okay. And since I'm evaluating it between 2 points, I don't need the c. And so now, can you evaluate that?
Then it would be, first part would be pi minus pi over 3. And then it'd just be subtract 0.
Right. That's one reason I did that, is because it makes this thing so much easier to evaluate. You really only have to evaluate the 1. So that's equal to what?
It would just be 2 that.
Then I got to multiply by that 2, so the area would be 4. 4 pi over 3, rather. Excuse me, the volume would be 4 pi over 3 of this paperweight. It wouldn't even be a paperweight. It would be more like an egg, an odd-looking egg.
Yeah.
Okay. What next?
We try some solids of revolution.
Yeah, that's a good idea. Where are those problems? Those are problems starting on 3. Actually, let's go to the next page.
Okay.
Let's do some on this page here. Let's do 15.
Okay.
Okay. So 15, the function is x equal tan of pi over 4y. And we want to rotate that about the y-axis. Let me kind of draw a picture here. So let's see. There's 1. Oh, we just want to rotate the area that's shaded.
Yeah.
Which is this area here. Okay, so after we rotate it, it's going to look like a top. How should we split this up in order to figure out its volume? What type of figure are we going to slice it up into? We got washers, we got discs, and we got, have you done cylindrical shells?
We haven't.
Okay,
So
we're stuck with washers or discs. How come
this would be a disc.
Okay. Integrated along which axis?
The y-axis.
Because the skinny part of the disc is the y measurement.
Yeah.
Not because it's being rotated about the y-axis. In other words, those aren't always the same. We're going to integrate along the y-axis because when we give our discs are horizontal. So the skinny part of the disc is dy. Okay?
Mm-hmm.
Okay. We started with a function of y, not a function of x. And that's good because when we integrate, if we're going to integrate with a dy, which we know we are, we need a function of y. So the function they've given us is just fine. It's a function of y. And we're going to integrate from where to where?
0 to 1.
No multiplying by 2 this time. In other words, there's the 0, there's the 1. So what's the integral of the tan of pi over 4y? Now, will you get to use your calculator on all of these?
On some of them we do, some of them we don't.
Okay. The integral of tan is not one that's easily memorized. Let me get my book out. I got a table that tells me the integrals. We know the derivative of tan is secant squared, but the integral of tan is actually the integral of tan of u is minus the natural log of the cosine of u. But we're going to have to divide also by this pi over 4, divided by pi over 4, like that.
Okay.
Okay? I'll explain that why later. The integral of tan of u is natural log of cosine of u, but the integral of tan of 4u would be natural log of cosine of u divided by 4. It's kind of the chain rule in reverse. You can't always apply it, but you can in this case here. You end up, I don't know how much time to spend on that. There's no way I'm going to teach you this unless you have some way of memorizing these.
No. probably a good idea not to.
Not to go into that. Yeah, I think we'd waste too much of the session on it. But just know that it's like the integral of cosine of 4x is equal to the sine of 4x divided by 4.
All right.
Okay, so the integral of pi over 4y is minus natural log cosine of pi over 4y divided by pi over 4, the coefficient. So this becomes minus natural log of absolute value of cosine of whatever the argument is divided by pi over 4 or multiplied by 4 over pi. Evaluated. Notice that we could test that premise by taking the derivative of that. If we take the derivative of that, we better get that. And you would. You'd end up with sine over cosine, which is tangent. So, and we still have to evaluate this from 0 to 1, but that's not going to be that hard.
Because the 0 will cancel out.
Well, actually, the 0 will be 1. I'm sorry, yes, the cosine of 0 is actually 1. The cosine of pi over 4 is square root of 2 over 2, and so forth. So we would be taking here, let's go through it. It would be the natural log minus the natural log of, well, the cosine of pi over 4, the absolute value of it is square root of 2 over 2. All times 4 pi. And let's put the 4 pi in front. Minus the 4 pi, another minus. Hardest part's keeping track of your minus signs here. And then when I substitute 0, this becomes cosine of 0, which is 1. So whatever that turns out to be is your numerical answer. And in this case, you would have to use your calculator to get what the log of square root of 2 over 2 is. I do happen to know what the log of 1 is. What's the natural log of 1?
0, right?
So this gets thrown away, and this is actually our answer. Minus 4 pi natural log of square root of 2 over 2.
Okay.
Okay. Let's do number 16. This curve, which looked like sine x, is actually sine x times cosine x. Okay, we're rotating it about the x-axis. So we create Humpty Dumpty here. How are we going to split up Humpty Dumpty?
Circles.
Discs, okay. Oriented which way?
Along the x.
Right, this way.
Yeah.
Because our function is a function of x. So we'd rather integrate it with a dx. Now, it's not to say we couldn't do it horizontally, but not easily. If we do it horizontally, we're going to have to integrate it dy, and then we're going to have to solve this for x, and that's not easily done. I wouldn't know how to solve that for x. If it was just y equals sine x, I could solve for x by, it would be the inverse sine of y. But when it's sine x times cosine x, I don't know how to solve that for x. In other words, we can only do this problem if we can figure out how to integrate with respect to x, not y. And it works nicely because we're going to use disks. Going to go from where to where?
That'd be 0 to 1, or 0 to... It's not actually marked on my book.
Oh, the red line tells you how to split it up, huh? Where else? What is this point right here? This point here is 0, but this point here clearly is not 0. What is it?
Is that 1?
No. Where is the sine times the cosine equal to 0 again?
I'm not sure.
At pi over 2. In other words, at pi over 2, this is 0. This whole quantity is 0 when x is 0, but the next place that it's 0 is when x is pi over 2, because the cosine of pi over 2 is 0.
Right. Right.
Okay, so this is pi over 2, even though it's not labeled on the curve. Remember, our domain is in radians. So we're going to integrate from 0 to pi over 2, and we're going to integrate this function because this is the radius of each circle, like that. Pi r squared, we always remove the pi. Okay? You with me?
Yeah. This makes
Okay.
sense.
Now the problem is integrating this thing. So we want to integrate sine squared of x times cosine squared of x dx. What can we do here to integrate this? As you know by now, it's not easy to integrate products.
Yeah. Would we split it up somehow, or?
Well, how about we use the Pythagorean identity to substitute for one of these and put it all in either cosine or sine.
Okay.
Let's put it all in cosine. So we're going to substitute for sine squared of x 1 minus cosine squared of x. So now we're going to integrate 1 minus cosine squared of x times cosine squared of x dx. Pi out there. Going from 0 to pi over 2. Now what?
I'm not sure how to integrate cosine squared x. Don't remember.
Well, we can break it up into, wow. I know how to do this, but I'm not sure you've been taught how to do this. Well, first of all, let's distribute this. So what we really have is cosine squared of x minus cosine to the fourth of x, which means I can break it up into two integrals. Right? See how I got that?
Yeah.
Okay. Now, to integrate cosine squared of x, you have to use the reduction identity. And I'll bet you have not been taught that.
No, it doesn't sound familiar.
It's basically the double angle identity. But it's essentially this. Now, why is that useful to use? Because I don't know how to integrate cosine squared of x, but I do know how to integrate cosine of 2x. Remember, the cosine of 2x is sine of 2x divided by 2. So when I change this cosine squared of x into this, I have something I can integrate. I can split that into two fractions, 1 over x plus cosine of 2x over 2, and I can deal with it easily. And I'm going to take this cosine to the fourth of x and break it up twice.
So it'd be 2 that with that quantity 2 multiplied by that quantity for the cosine 4x.
Yeah. You have to just keep breaking it up.
Right.
In other words, that's cosine squared of x times cosine squared of x, so it's that times the other. Distribute them, multiply them together. You end up with cosine squared of 2x, then you use this identity again. In other words, it's fairly tough. This might be a problem there where they would give you your calculator to let you solve it. The key to this problem really is probably determining what the limits of integration are. In other words, because I don't think you've probably been taught how to do this integration. And I know how to do it, but I know that it doesn't get taught until Calc BC.
Yeah, it doesn't seem familiar.
I don't really want to go through all of that with you. And some of the problems you're going to be allowed to use your calculator to solve the integral, and this would be one of them. I'll just say that. We'll leave it at that. But as long as you know how to get these limits of integration, it might be tempting to think that's pi instead of pi over 2, because the sine curve looks like this. And that's pi. But this is not the sine curve. This is sine x times cosine of x. So we have to figure out where sine x cosine of x is equal to 0. Obviously, it's equal to 0 when x is 0, because sine x is 0. And again, it's the next place that one of these things is equal to 0 is at pi over 2, where cosine of x is equal to 0. All right. What else can we do? You've had some washers?
Yeah. That might be a good review.
The only problem is we don't have any problems that you would break up into washers. Let me find one. This is why I really kind of need you to bring the problems to me, because for me to pick out problems may be beyond the degree of difficulty that you're dealing with.
Right, sorry. I'll try to do that next time.
Well, yeah, as a normal process, it probably works better. Let's look at 23, which is y equals x squared plus 1. And y equal x plus 3. Well,
okay.
Let's graph those. That's just a regular parabola shifted up by 1. So it looks like that. This is a linear equation going through this point, 3, and has a slope of 45 degrees. So it's basically that. And they want to revolve this about the x-axis.
So we'd have to use washers for this one.
Yeah. I'm not a particularly good artist, so it's going to be hard for me to draw this, but I think you can see when you use washers, you have to be concerned with the inside radius and the outside radius. So when I revolve this shaded area here about the x-axis, this is my inside radius of the washer, and this is my outside radius. Right? Can you see that?
Yeah.
And then everything in here is going to be solid. And that's the solid part of the washer. Let's see, I guess I can figure out how to draw this. So here's our solid looking figure. Excuse me. That's our hole. This part down here is the hole of our washer.
Yeah.
In other words, when we rotate this region about the x-axis, I have a giant hole in the middle of the resultant solid. And the hole is defined by, let me put a different color. There's the hole. The solid part is this part. Right? In other words, there's the figure. That's result. I don't know what holds this solid together because there's nothing holding it together. But that's okay. It's a calculus problem regardless. So we're going to integrate from this point here to this point here. How do we find those 2 points?
We should define the intersection.
Okay, so how do we get that?
We typically can use our calculators for these sorts of intersections.
We set this equal to this. Because that's where these two functions intersect, is whenever these are equal to one another. So I'm going to say x squared plus 1 is equal to x plus 3. And I can solve that. That's a quadratic. It's going to give me 2 answers, which is what I'm looking for. That'll be my limits of integration. So this point here is minus 1, and this point here is 2. So I'm going to integrate from minus 1 to 2. What's the area of each washer?
It'd be pi the larger radius squared minus pi the smaller radius squared.
I can factor out the pi and put it outside, so I'm left with this dx. Okay. What's the big radius?
X plus 3.
And the little radius?
X squared plus 1.
Now, integrating this is, actually it's going to be a piece of cake, because let's see, when I square this, it's very easy to integrate stuff that's being added and subtracted. It's just hard to integrate stuff that's being multiplied. So I want to multiply this out. Notice the x squareds go away, and I'm left with integrating 6x plus 10 dx. What's the integral of that?
It'd be 6x squared over 2 plus 10x.
Evaluated from -1 to 2. And I know you know how to do that. Okay. So we've done our disks. We've done disks in integrating along x and y. We've done washers integrating along x. We've done cross sections integrating along x. We got about 20 minutes.
Okay.
Don't go up to exercise 39 because that gets into cylindrical shells. That's something like 25.
Okay.
Or would you rather stay with polynomials and stuff?
It might be good practice to do some trig stuff with this as well.
Okay. All right. So let's always, I would say always graph it. I mean, maybe you can get away without graphing it sometime, but graphing it really helps you to see it. So secant of x. Secant is reciprocal to what?
Isn't it
Sine.
secant x tangent x?
Sine.
Sine. Oh, it's reciprocal, sorry.
Right. Because I want to know how to draw it. Okay. So that's the first part of the secant x. This is the next part. That's one cycle of secant x. Let's erase the sine part. So there's y equals secant x. Of course, that goes on forever. But and the line y equals square root of 2. Well, what's this value right here?
Is that pi? I don't quite remember.
It's 1.
1.
In other words, when I drew my sine curve, the peaks and valleys are 1 to 1 to -1. So this value on secant has to be 1 right there also.
Right.
And this value is -1. So the line y equals square root of 2 has to be above here, because square root of 2 is 1.4. So there's the line y equals square root of 2. In other words, this is 1.4 here. Okay? And we're rotating this whole thing about the x-axis. Actually, not either of these. Well, let's see. It says to go from minus pi over 4 to plus pi over 4. Okay. Minus pi over 4 is there. Plus pi over 4. Well, let's see. This was pi over 2, because that's where the sine gets to 1. So this has got to be plus pi over 4 right here. Well, the only part in this thing that's bounded is this part right here. Right?
Yeah.
In other words, the area enclosed by the line y equals square root of 2 and y equals secant of x is this part here. Ooh, unless they want, they might want the bottom part here. I think they do. No, they don't. Enclosed by this area, so it's got to be this part right here. So we don't need to consider any other cycles of secant. And I'm not sure why we're going from minus pi over 4 to plus pi over 4, because we should be going from 0 to pi over 4, because there's no area up here that's enclosed. Notice that the rest of the secant is down here. So this does not enclose any area on this side, unless they're trying to say that all of this is enclosed. They might be. They might be. In other words, they may be talking about rotating all of the shaded area about the x-axis. Let's assume they are talking about that. Because if you connect between y equals square root of 2 and this part of the secant function, this is all enclosed by it. And there have to be some reason why they're going from minus pi over 4 to plus pi over 4. Because if we were just rotating this part, we'd go from 0 to pi over 4. So we're going to rotate the whole thing. We're going to go from minus, and it's not symmetrical this time. Notice. I can't just go from 0 to pi over 4 and multiply it by 2. This is a much larger volume stuff here than this little tiny bit is up there. So let's see. After I rotate it, we're going to use washers or discs?
This would use discs, I believe.
Well,
because I don't think there's a gap.
Well, there actually is going to be a gap on this part of it. In other words, after we rotate it, there won't be any gap here. This will be a solid figure. So we're going to use discs going from this point right here, minus pi over 4, to 0. We're going to use discs. But then when we go from 0 to pi over 4, we're going to have a gap here. We're going to need washers. We have an outside radius and we have an inside radius. So let's do this in two steps. Minus pi over 4 to 0 for secant of x dx, because we're definitely integrating along the x-axis. The skinny part of our discs are vertical. They're perpendicular to the x-axis. And then we're going to also add to that the volume that we get from rotating just this little corner part up here, I presume. And that goes from 0 to pi over 4, same function. Not the same function. In other words, we use discs here, so this was pi r squared. And over here we're going to use washers. So this is going to be pi, well, the outside radius squared. What's the outside radius?
Is that the square root of 2?
Minus the inside radius, which is secant x, quantity squared. No, excuse me, it's the inside radius squared minus the outside radius squared. So it's this squared minus this squared, which is good because it's easier to integrate. This is just the integral of 2, so that becomes 2x. And the integral of secant squared x, oh gosh, that's another one of those difficult ones to do. I know how to do it, but showing you how to do it, I don't want to do that. It takes too long. This must be one where they're going to let you do by calculator.
Probably.
Yeah, so just put that into your calculator. The key on this one is knowing to break it up into disks and washers. There's an example of a problem like that in here. Let's find it. Well, maybe I'm sure there is. Gosh, I cannot remember where it is, though. Must be in my other calculus book. I remember what it is. It's if you rotate this figure about the y-axis to create, this is some function, I don't even know what it is, it doesn't matter. We'll just say that's f of x, the curved part.
Okay.
This is x equal 3. So if we take some function that looks like this, and it's bounded by x equal 3 and the x and y axis, in other words, we're rotating this part here about the y-axis, we're going to create a shape like this. And notice that this, we're going to use disks, but horizontal disks. For going from here to here, we're going to use disks. But going from here to here, we got to use washers, where we have an outside radius and an inside radius. Which means this better be a function of y, not a function of x. Because we want to integrate it along the y-axis and in 2 steps. Now, you could theoretically say you could integrate the whole thing in 1 step, but you'd have to change your inside radius at this point. So really, you're going to have, if you're going to use disks and washers to integrate this or to slice this object up, you're going to have to do it in 2 steps. One step's using disks from here to here. The other step, use washers from there to there. Add the 2 things together. Once you learn cylindrical shells, you can do this whole thing in 1 step. It's a completely easier process because we can do it in 1 step instead of 2 steps. But from what you know at this point, you would have to do this in 2 steps. Because there's no inside radius from here to here. It's all disks. That's a disk, 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 disk. Once I get up into here, now I got washers with an inside and an outside radius. Okay.
Okay.
Yeah, let's do one more cross-sectional.
Okay.
Let me find a good one. Number 7 on page 391. We'll do that problem and we'll be done. Okay, so notice that when they draw these cross sections, they put the x and y axis diagonal to one another so that they can get an accurate drawing of it. that is y equals sine x. This is the x-axis. This is the y-axis. And we're going to cover this thing in equilateral triangles. What is going to be our axis of integration?
Along x?
Because the skinny part of these equilateral triangles is perpendicular to the x-axis. So we're going to integrate along x. Okay? We're going to go from 0 to pi. Here's our triangle that we're looking at. What's the area of each of those triangles?
So the would be the function squared divided by 2. So it would be the function squared divided by 2.
Y divided by 2. The base of this triangle, the base is sine x, and this would be sine x. So what is this height? Because the area of this triangle is the base times the height.
Yeah.
It's 1/2 the base times the height. So if this triangle, if the base is sine x, what's this altitude equal to? It's a 30-60 triangle. That's 60, that's 30. So we know the altitude is always equal to the square root of 3 times this length here, which is sine x over 2. So this altitude is sine x over 2 times square root of 3, because our similar triangle is 1 square root of 3, 2, and our one side is half of sine x. So there's our one side multiplied by square root of 3 gives us this altitude. So the area of the triangle is 1/2 the base times the height, and the height is this. So what we end up with is square root of 3 over 4 sine squared x. Again, that's a calculator one, because you haven't been taught how to integrate sine squared x.
No.
All right. That's a good place to stop. When's your test? Or are you reviewing for is this for the AP test?
I think so, yeah. And then our final is like a week or two before that, so.
Okay. So you're kind of reviewing for your final and at the same time reviewing for the AP test.
Yeah, exactly.
The AP test is going to cover everything from limits through differentiation through integration. So when you and I get ready to review for the AP test, the best thing you could do is bring me the review material your teacher gives you.
Okay.
I'm sure she'll give you something. Might be like 3 pages of it, but what you'll want to do is take a picture of each page and send it to my email.
Okay, I can do that.
And then we'll have it to draw from. As far as reviewing for your final for your class, I would think the teacher would do the same thing, but maybe not. I would think she would give you a review sheet for either one. Otherwise, we're just going to have to take a 60-minute session and devote, 10 minutes to limits, 10 minutes to differentiation. But it would be much better if you bring the review material, so we'll know what to cover.
Okay, I can do that.
The scope of calculus is just too broad. I wouldn't know how much time to spend on limits and how much time to spend on optimization, with differentiation and related rates and all the various topics of calculus.
Right.
Okay? All right.
All right,
So,
thank you.
You're welcome, and I will talk to you next time.
Sounds good. Bye.